are now talking about host security, and I started out by saying we really have to understand what the adversary is going to do on our system once they get access to it. So I went through this, what we call the attack lifecycle of an adversary. So these are the actions that they would typically go through when compromising a host. And so what we'll do is we'll finish off the attacks, and then we'll talk about all the different defenses that have been developed to try and address the fact that these attacks are happening. And this helps you understand why there are all these different security products on the market, because it's vast, the products, and they align with trying to prevent different steps of this attack life cycle. So we started with the initial compromise. And then we're in the middle of the privilege escalation part of this. But the other things that we're going to cover are the reconnaissance, the lateral movement, and then finally the maintenance of presence, and then the actions on objectives. So we're going to talk about all of these different things. And then we're going to talk about what would you do to mitigate these attacks as a defender. That'll be towards the end. Okay, so we're in the middle of privilege escalation and the different things that you can do to escalate your privileges on a system. And I should note that this is one of the two parts of this that I'm going to do a deeper dive into, because this is part of your lab exercises. So everything else, I'm just going to give you an overview, but I am going to talk about the specific privilege escalation techniques that show up in your exercises for this week. Okay, so we got all the way up to this dirty pipe vulnerability. And the dirty pipe vulnerability is one in a very long line of vulnerabilities that deal with the kernel. The kernel, the Linux kernel, is one of the most complex pieces of software ever written. And if you're at this level, it's inevitable that you're going to be programming bugs into this system. Even like the best software developers have difficulty handling the level of complexity it takes to build a high performance operating system. And so this is one of the things that was identified in 2020, earlier this year, actually, which is why I put it in here, because it's very relevant. And so any kind of implementation bug that you have in the operating system, because the operating system is running at a privileged level, that ends up allowing the adversary to get full-on compromise of that system. And this is what dirty pipe is. So I'll just go through the details of dirty pipe, which is one of your labs. The idea of dirty pipe is to leverage vulnerabilities in the implementation of pipes. So we used pipes earlier in the Linux files, in the Linux subsection of this class, where you're taking the output of one sort of file descriptor and sending it in as the input of another file descriptor. And that's called a pipe. And in the operating system, you have to build that abstraction in the kernel for it to work. And that's what this picture is showing you. So when you do a pipe in either the program or in the shell, you have a file descriptor where the output of one file descriptor gets sent through the pipe and is used as the input of another file descriptor. And that's an example here. And this pipe could go to and from the exact same process, or to and from the same code. But typically you would pipe from one process to another, but in this case, you could set up a pipe between two of your own. Okay, the way pipes are implemented is via kernel memory pages. So you need some kind of buffer, because when you write into a pipe, you might not be able to read from the pipe until a little bit later. And so underneath this in the kernel, the way this works is that you have a set of pipe buffers that are allocated. And so this is sort of like the entry, the page entries in the kernel. And then each one of these pipe buffer data structures points to the actual data in this page that will sort of hold the data in the pipe. So this is a circular, it shows it as a circular array of pipe buffer entries that point to the actual pages. Now you can, because this is a pipe and you're reading data, or you're getting data from one end and reading it to the other, pipes naturally should be implemented with this append flag, right? To allow the pipe to keep adding to a page, because you never know how much more data an attacker process is going to send through there. And that's in yellow. And so there's a special flag that says for this particular page, allow appends, because it's a pipe. So that's what the yellow is denoting. And then you can, by having this flag set in this pipe buffer structure, you can then, without additional privileges, just add more data in red to the page that backs this buffer. Okay, so that's the first step. So with dirty pipe, the adversary basically creates a pipe and then loads it with pages that all have that flag set to yellow. And so you see here, all of the structures in this process to implement this pipe are all have the append flag set. And then this is allowing you to then append to any of these pages to implement this pipe. Okay. There is a bug in this implementation, is that if you decide to create another pipe, the pipe buffer structures that are then reused, so these things are shared across any of the pipes of this particular process. So if the attacker creates a new pipe and these flags are set in the original pipe buffer, they don't get reset. So that was the implementation bug. They didn't go and clear the append flag from any of these pipe buffer structures after the fact. So that's the bug. And so there's a system call called splice that allows you to splice to a file through a pipe. And that's what this thing is doing. It's splicing to a file, and the file that it's splicing is a read-only file that's owned by root. Now, the page cache, the permissions for this should be denied if you actually did this right. But what you're going to do is you're going to use something underneath it to basically append to a page that is going to poison this file. And that's the bug. So the page cache should disallow this directly, but because you have this other mechanism, this append mechanism through a pipe buffer, what happens is that you can actually use this pathway to append to the page, and then the page cache is going to see that the page got modified. And even though you opened up this file as read-only, in the kernel, it's like, oh, I have a page that's dirty. I'm going to write it out to the backing file. And so the permission check here is bypassed by you going straight to this pipe buffer. And because this was a set to append, this actually makes that page cache get written, or poison page written out to the actual original file. And so this is a file owned by root, and you've been able to modify it directly as an unprivileged user. So at the highest level, that's the exploit in the lab for this week. And I just wanted to explain this. There's an article that does a deep dive into the kernel structures that allow this to happen. I don't want you to have to like read that, but this is effectively the bug, and it's just an implementation bug. The fix is super simple. You just clear this flag whenever you're done with those pages. Okay. The other set of privilege escalation flaws that are really becoming common these are flaws that are really hard to get rid of. And this is basically flaws in the hardware that are difficult to fix. And the one that I'm going to talk about is flaws related to DRAM. So dynamic memory requires a continuous refresh to hold the charge. So the way DRAM works is that there is a gate that is in front of a capacitor, which is like a battery. And the way you store zeros and ones is to either store a charge there for a 1 or to clear out the charge for a 0. Now, the problem with storing a bit as a charge on a capacitor is that capacitor leaks. And so eventually you have to refresh that bit in order for you to maintain the state of that DRAM. Now, rowhammer is a vulnerability that in DRAM, all of these capacitors are basically right next to each other. If you can choose to hammer a row on one side of a capacitor or on the other with a specific bit, you can flip that bit if you just hammer that row over and over again. And so bit flipping attacks, you might think that these are sort of like low impact things because, you know, if a bit gets corrupted, then won't that crash the program? The problem is that if you can target a bit flip, and if the adversary has the ability to target a bit flip, it can find the one bit that it needs to get ownership of your machine. And that's basically what rowhammer is. And so this is a picture of it. You're hammering each side of so the row here is in between the two green rows. And then you're hammering the green rows in order to flip a bit in between these two rows. And the ones in between will get flipped at a higher rate than the ones sort of on either side of this hammer. So,
by proximity?
Yeah, by proximity. Yeah. Yeah. So this is where the DRAM, and you could actually, so this is what the adversary is trying to do. If the system knows that this is happening, the countermeasure would be to refresh all of those bits at a higher rate so that the hammering, so this hammering over time will get undone more quickly. So your refresh rate has to be a little bit higher.
Okay. This is a temporary, like the bit flipping via rowhammer is temporary.
Yeah, and it's
like until those bits get refreshed.
It gets refreshed, yeah. So what happens if you could flip a bit in the UID, right? This is a single bit flip. And if you can find the place in the kernel where a process's effective UID is stored, you would flip that bit and then get root. And some of these advanced rowhammer exploitations know exactly where to hit the row. Now you actually have to figure out, you have to reverse engineer where in physical memory those bits that you want to flip are allocated, because all you have, you know, is the virtual memory addresses. So there is some engineering involved in order to actually target the right area in memory. But this is one of the ways that you can do privilege escalation that's going to be really hard to get rid of. And so people have talked about different countermeasures for this. And then there's been several cycles of countermeasures and then counters to the countermeasure that undo that countermeasure. And so this is an attack that's basically sort of in the news in terms of a privilege escalation one over the last several years. Okay, so that's just a sample of some of the privilege escalation vulnerabilities that an adversary might use as soon as they have access to your system. The next set of activities that an adversary might do on that system is to do reconnaissance, internal reconnaissance, not only on the machine it's on, but across the enterprise, what other machines are running that you might be able to hijack. And so one of the easiest things the adversary can do is to attempt to do credential collection on the machine that they're on. So if there's ability to access Etsy Shadow, you can get all the password hashes. And then you can do basically what you did in the previous labs. You know, you can crack hashes based on their format. You can do the dictionary attack against those hashes. You could do in-memory credential dumping. So if you are on a system where the credential verification is being done by a process, which it usually is, that process has to have those credentials somewhere in memory unencrypted. And so what you can do is you can just go directly access those memory locations, especially after you have elevated your privileges. And then you can find everyone's credentials sitting there in memory in like an authentication process or an authorization process. And there is a Metasploit plugin called Mimikatz that basically took this to the nth level. It basically had knowledge of how all of the credential handling pieces of software worked on Windows. And then you ran this one thing and it just pulled all the credentials it could find in memory and then dumped them for you. So Mimikatz, Pass the Hash, these are all tools that allow an adversary, once they're on your system, to get everyone's credentials that it can in memory. You could also look in the file system. So for example, on Linux, on Ada, on linux.cs, it's like people have their SSH keys in there. So if you have root access to that file system, I can get private SSH keys of everyone's within everyone's directories. And then if you've enabled SSH access using that private key to your GitHub or your GitLab or anything else, I can get access to those as well by just dumping those SSH keys. If you've put credentials in scripts, for example, and so if you take the cloud class, you're like, don't put credentials anywhere in the file system is the idea of that class. Is like, yeah, you don't want to put it in your code and you don't want to put it in a script because that's in the clear. And then somebody getting those credentials can just, act as you. So that's another thing an adversary will do. If you have a web browser session and you basically have cookies lying around or OAuth tokens lying around, the adversary will scan for those and then hijack any of those active sessions that you might have. So this is all part of credential collection that an adversary will do. And so you could think about, yeah, if an adversary escalates privileges on that Linux, the Linux machine, our cluster, and collects all the user's credentials, that has very high impact. You can also, if you don't have it instantaneously there, you could just wait until the user actually does the authentication or accesses the sensitive site by just doing runtime key logging, screen grabbing, or even access to the web camera or microphone continuously. And all of these have been used in the wild by nation states, for example, and by criminals to basically get access to user information in real time. And so Metasploit and Cobalt Strike, these are toolkits that adversaries will run on a compromised system in order to get you these pieces of functionality. So the malware supply chain of tools is quite robust. And then this is the kind of stuff that they would deploy on that system as soon as they got access and privilege escalation on that system. They would do these kinds of tools. The other thing that they would do is the traffic monitoring. So the stuff that you were doing with Wireshark, they would do that too, to look at all the different connections going across the network, because then that allows them to see, well, what is the architecture of the running enterprise? And can I find different targets based on the connections that are going to and from this host? So that's what Wireshark and the LSL lab will kind of showed you. And then you could do something more active, which is what your Nmap stuff is doing, to actually discover vulnerable hosts. And then you could also, you could pair that with discovering vulnerable services. And one of the things that Metasploit will do is both Metasploit and Nmap will allow you to probe services for vulnerabilities automatically. So Metasploit will be like, oh, here is a Windows file sharing service running on that port. I know I have a library of exploits for that service. I'm going to see whether or not this particular host is vulnerable to any of them. And then it will just, to the adversary, it will just identify the exploits. And the exploits are basically built in as libraries to this tool. Then you could actually, in the same tools, in the same session, actually launch the exploit. And this is something, if you take the web and cloud security class, there is one lab where we weaponize an exploit and then hijack a running system at the very end of that class. Okay, the next step of the process is to move laterally. So once you have identified a host that you can use as you can use your current machine as a stepping stone to attack another machine, you would then move laterally to that other machine. And that's what lateral movement means. So you could find the SSH keys and then use the SSH key to SSH into a different machine, remote desktop. So if you have a Windows credential, then maybe you can do a remote desktop to a different machine in the enterprise. You could actually, if you got the right credentials, you can pivot over to a domain controller. And the domain controller is a Windows-specific thing that basically holds all the authentication information for everyone in that enterprise. If you're using the domain controller to authenticate all of your employees, that's typically, this is like the goal the gold standard for getting complete access to an enterprise is to hijack a domain controller. You can move to any shared drives. So if you have access and if you want to drop like a Trojan or some piece of malware that everyone in the enterprise can then run, then you could look for shared drives that you have access to and try and copy those payloads into the shared drives for people to see and click on, basically. And then any other vulnerable internal server that you've nmapped or Metasploit scanned, you can just pivot right over to that. The next set of techniques that I want to talk about is maintaining presence on the machine. After you've compromised a machine, you want to be able to outlive and stay on that machine as long as possible. And so that's the idea, is the longer an adversary is in your network, the harder it is for you to kick them out. Because what they're doing is they're moving laterally and they're implementing things to allow them continued access to that machine. And it's going to be difficult for you as an enterprise to be able to, in one shot, wipe out all of the or re-image all of the affected systems all at once. And so there are multiple ways that the adversary can maintain presence on the machine. The two that I'm going to talk about are the backdoors and the rootkits and Trojans. Rootkits and Trojans are covered in depth in the malware reverse engineering course, but I'm going to talk briefly about both of these things. And so one of the things that you could use, an adversary could use to maintain access to a system, is to use the built-in facilities for running scheduled tasks. And so on Linux, the way to do this is with a service called cron. And so cron allows you to execute a command at a scheduled moment in time. And it's a very useful facility for doing things like backups. Like if you're going to do a nightly backup of your system, you're like, oh, I want this system to wake up in the middle of the night when no one is using it, and then to run a job that basically takes the file system and backs it up over the network somewhere else. And you can do that using cron. Regular users on that system can also schedule tasks using this cron tab command. And so an adversary can basically insert cron jobs inside of your system to wake up and do a malicious task. And that's why we're covering it here. And this is a way of basically implementing a backdoor. So there are places for you to look at to see what scheduled tasks are being run. The first location is in these preset directories in Etsy. So in Etsy, cron dot either hourly, daily, weekly, and monthly. These are jobs that get run at these intervals. And so if you're an adversary and you want to run something hourly, maybe you can drop in a rogue file in Etsy cron.hourly and then be able to get that persistent access. The good thing about this is that your malicious process won't be continuously running. It might only run, for like maybe a couple of seconds every hour. And then the defender is going to have to make sure that if the defender is scanning all the processes running on that system, looking for rogue processes, the defender is going to have to wake up at the exact same time that the cron job is running in order to detect something is happening. So that's a sneaky way of installing a backdoor. Another way of installing backdoors is to do a per user cron job. And so in order to do that, there is this cron tab-e command that allows a user to edit and store a cron job. And it basically brings you up into an editor. And in this file, there are basically 4 fields per line that specify the timing of the job that you want to create and run periodically. And so the first field specifies the minute at which to run. The second field is the hour. The third is the day of the month. The fourth is the month to run it. And then the fifth is the day of the week, if you want that kind of a schedule. So that's what each one of these is denoting. And so an example line in a cron tab is something that looks like this. So on the 15th minute, of the third hour on every single day of every single month, on every single day of the week, I want you to run this command. And then this command is basically invoking a script and sending the output to different files. So that's basically what the semantic of a cron tab is. So this is one way. If this script is actually doing things like, oh, exfiltrate the logs of this system, then at 3:15 in the morning, every day, you'll get the logs exfiltrated, if that's what this script does. Okay, other questions about cron? This would be just one of the, like, you're gonna have to do an audit. Like, if your system is compromised, you're gonna have to look here to make sure that the adversary hasn't tampered with this part of the system.
If you don't need root to set up cron.
Yeah. So if you set up a user cron job, you will run as the user account. If you actually need to run as root, then yeah, you would have to somehow get root privileges, install it on the roots cron tab, or you would put it in one of these directories because these will run as root. Any of the jobs here will run as root in these directories.
Just thinking, like, you could set up a cron. If it ran as root, but you were not root, then you could like have it just do a reverse shell or something.
Yep, you could. Yeah. So if you escalated privileges, you could do a revert. You could actually run the backend as root, the shell as root, and then connect up to somewhere else. That's correct.
People have figured it out.
Yeah. Well, so this is one of the reasons why you have to be monitoring the cron tabs. Everyone's cron tabs in this directory, and then all the files in here. And this will, when we talk about intrusion detection systems, that's one of the things that they have to monitor. And then you have to alert on changes to these things. But then if people actually are legitimately changing their cron tabs, you don't want to see those. But that's the issue, that you could basically hide yourself here and then force a defender to have to look at all of these different things that are going on, which is something, yeah, tools have to do. Cron tab editing is so rare that when you see it, you might, immediately be suspicious. I suspect a lot of users aren't messing with their cron tab every day. Okay, another way to hide is through the system startup process. So we talked about the Linux process tree. One of the parts of the Linux startup sequence is this init process, which is process number 1, is going to go through and examine all the different services that need to start up by default when you boot the operating system. And that's done. And so this is an example that we used earlier, where the init process basically spawns off the login daemon, right? Like for multi-user logins, there needs to be a process running that allows people to authenticate and get a shell. And so this is just one of a whole bunch of different system processes that the init daemon is going to start up. And so this shows a picture of init. There's also an alternative to init, which is called systemd. And systemd is often used on newer Linux systems. And so based on whether or not you have one or the other, the adversary could automatically start up any malicious code that it wants to by inserting itself in the startup sequence is the idea. And as a defender, you have to look for this, right? And you have to validate that everything that's being started is legitimate. So this is the idea. I'm just going to cover systemd. And this is the system and service manager for Linux that basically is intended as a replacement for the old init way of doing things. With systemd, the services that get started up by systemd are specified via these unit files. And I'll show you a picture of a unit file. This is an example of Nginx. So if you install the Nginx web server on your Linux system, what it's going to do is it's going to set itself up so that it automatically boots whenever you boot the operating system, because the web server, you don't want to have to start your machine and then have to go and start Nginx manually. And so if this is intended to be a web server, then you would install the Nginx unit file in systemd so that the systemd daemon will automatically start Nginx on boot. So this is, so in etc systemd is where these unit files are stored. And then in this particular sort of subdirectory, it's hierarchically organized. So to allow the users to specify how it wants to start, like what conditions should it automatically start. And so in this case, you have this Nginx service unit file that starts whenever there is a multi-user booting process that's being desired. And then this is what it looks like. You have a description of what this service is. And then you have basically commands that will automatically run when the service is started, stopped, and reloaded. And then these are places where if you wanted to basically inject like a backdoor service, you could actually run that as part of the Nginx startup process. And so these are just regular shell commands that you could basically modify. Okay, another way of controlling these services through systemd is through a command called systemctl. And this is just your command line interface to configure systemd services. And so the systemctl command will return information about any of the services that are running on your backend. And it allows you to invoke different commands in the unit file that we showed here. So yeah, you can actually run any of these things using the systemctl command. So here's an example. So we'll start with Nginx again. Systemctl status on that service. And this will basically give you the status of this service currently running. And so this is where you can say the service is enabled, it's actually running. And then this is the basically the PID, and the PID of the worker processes, the PID of the master process, and you can get actually error information using this status command. So all of the error messages are sent through, are accessible through systemctl as well for this daemon. You could use systemctl to stop the daemon, to start it, to restart it, and then to reload it. And so these are all ways of interacting with that systemd service. You could also use systemctl to look at whether or not this service is enabled and to either enable or disable the service on boot. So here's an example command that says, you know what, across all of the services that systemd manages, give me all of the ones that are enabled. And so this is where this lists all the unit files that are set to be enabled, and you can see all the different services that are running on this backend, including things like cron. You can individually disable and enable services by using just their name, and then it'll basically take the unit file out of the startup process if you disable it, or put this unit file back into the startup file using enable. So again, on compromised systems, this is where adversaries might tamper with the startup process in order to always run, right? And this is a natural way to get persistence on a Linux system. Windows has the exact same thing, where it has a startup process that you can inject your rogue code into so that you're always running on a Windows machine. Okay, the next thing you can do is to install Trojan software, so Trojan binaries or Trojan libraries. And so here's an example where you would basically drop malicious files into the running system to tamper with the files that the compromised system will eventually access. So here's an example of WannaCry, where you arrive as an exploit and it looks like a binary that's legitimate. And then you trick the system into running it. And then this is the thing that will basically drop ransomware, encrypt all of your files, and then basically disable the system. So there's one example. Here's another example where you drop an infected document, and it basically is attempting to launch an infected service host.exe. So this is your legitimate thing that got Trojaned, replacement. So it's basically service host, which is just a standard Windows process for running services. And then this particular load info thing will basically run that legitimate process in a Trojan. It basically will load rogue data into this legitimate process and run the malicious payload. This particular exploit actually relies on the next thing that, so this is a file tampering thing. This is an example of a process tampering thing as well. So another thing an adversary can do is to take your running service host process and then to get via privilege escalation to get access to be able to attach as a debugger, for example, to that target process. And then with those privileges, for the adversary to then inject rogue code into the running process. And that basically Trojans the process in place rather than doing it in the binary or the library level. You're actually taking the running process and turning it into a zombie in this case. Another way you could do process tampering is through something called process hollowing. And the idea here is to take that legitimate program, service host, and to launch it in a suspended state. And so this is there's flags in Windows that say, run this, load this binary up into memory, but don't start execution immediately. And then this will basically give you a stopped process that is a legitimate process. And then what the adversary will do is it will connect up, again, as a debugger to this process, and then basically deallocate all of the code and the data of the legitimate process, and then write into it instead the malicious code. So you're hollowing out the process, the legitimate process, and then you're completely replacing it with malicious code. And in this way, it actually looks like a legitimate process, but all the insides of it are basically replaced with your code. Okay, are there questions about this? Because this is another technique that the adversary will use to maintain presence on that running system. Okay, the last thing in this process is to complete the mission. And so there are examples of this. Crypto mining is one thing they could do to monetize access to your system. That's actually the one you want them to do, because this does the least damage to use as an enterprise. If they're just stealing your CPU cycles, that's actually a good thing. The more severe thing is for them to monitor all the data and then exfiltrate sensitive data. And so things like keystrokes, browser history, database records, network traffic, these are all things that are very impactful to an enterprise. The other thing they can do is take that collection of machines that they've hijacked and then turn them in, make them part of a botnet that they all control. And so this is where the botnets for sending spam and DDoS are, which we covered earlier. That's what they're used for. And then finally, and this is the most prevalent thing that they'll do, they'll basically do ransomware. And so the idea of ransomware is to get onto that system, generate an ephemeral secret key, and then encrypt all of the data on that machine with this ephemeral key, and then delete the key. And delete the files, and then delete the key. And then assuming the adversary has kept that secret key, then you ask the victim to pay money for that secret key to be revealed. So this is very prevalent. There's a whole bunch of different variants to ransomware. And one of the things that is kind of new over the last several years is to take that data and then rather than encrypt it and deleting it, what you would do is you would just say you would prove that you own this data and you would threaten to reveal it unless payment is made. And this is what happened with the Uber breach. The adversary took all the data. They were like, hey, Uber, pay me money. Otherwise, I'm going to reveal it. And Uber paid them money and then just assumed that they would not reveal it, is the idea there. And this is actually much more powerful because If you have figured out how to restore from backup really easily, then you could be like, I'm not paying you. But if your business depends upon the data that you have being private, remaining private, then it's much more likely that an enterprise will pay the ransom. Because if you do have a data breach, there's all sorts of stuff that you have to report, and then it tanks your stock price. And this is what Uber was trying to avoid, that ended up getting the CISO convicted, because they were trying to cover up the fact that they had a data breach when they were required by law to basically expose it. And so they tried to reclassify that data breach as a bug bounty. And then they're like, we don't have to report that because we're going to pay this adversary as a bug bounty finder. But that whole thing blew up in their face. So that's where that thing happened. And so this is basically what's going on just over and over again. Adversaries are attacking all of these places that aren't ready to resist an attack on ransomware. And so this is basically hundreds of millions of dollars of damage being done basically on a daily basis. Okay, so that ends the attacks. And I'm going to start the defenses against these attacks next, because now that you know what an adversary is going to do, there are a number of things that you would want to do as a defender to protect against these things. And so we're going to next talk about the host defenses against these particular attacks. The first set of defenses are what I'm going to sort of lump all in one. This is basically a monitoring approach to detecting adversarial behavior, and then runtime monitoring followed by immediate remediation is the idea of this defense. And this is where a huge amount of vendors are basically selling products in. So it started out as this thing called intrusion detection systems. And then they were like, well, we want to do more than just detect compromises. We want to prevent them after they've been detected, or prevent further damage after they've been detected. And so then they developed these intrusion prevention systems. And then now we're trying to add even more in terms of the amount of data that we're using to both detect and prevent intrusions. And so now the buzzword is EDR, which is endpoint detection and response. And all of these things are labels on the exact same thing. And so that's what we're going to cover. And so the idea is to just monitor your endpoint and then detect and prevent adversarial access is their approach. So with intrusion detection, you're basically scanning everything that's coming into your system, and you're monitoring the behavior of everything running on your system. And if you see known malicious activities or anomalies from known good activities, then you'll settle an alert and then inform some operations team that something has happened. The intrusion prevention system is basically an IDS. So the acronym for intrusion detection systems are IDS. The intrusion prevention system, or IPS, just adds policies to respond automatically to prevent further activity on your system. And so one of the issues with IDS systems, intrusion detection systems, is that you send an alert, but then you're waiting for some security engineer to do something about that alert. And the adversary knows that if there's a human in the loop, all you have to do is send that human thousands of alerts, right? And so this is a strategy for an adversary, is to just get in there and send a whole bunch of bogus alerts to an administrator, and then the administrator will ignore it. And so intrusion prevention systems had been developed to basically take all those alerts and then act upon them automatically to save the operator some time. And then these two things were combined, and now they're referred to as these EDR systems, this endpoint detection and response. And so here's the workflow for EDR systems. You identify things as they're happening on your system. If there's incoming payloads that you can scan, then you scan them and eliminate them. So this is part of the protection. You can detect when stuff gets through and then identify compromises, and then you can automatically respond. And then if you're really advanced, you can automatically recover from all of this. And this is what EDR is attempting to do on the back end. Okay, so that's the general approach for EDR. Within this EDR system, there are a whole bunch of techniques that you'll use to do this activity. The first technique is to do signature detection and block lists. So the idea here is that you have a library of known bad content, and you look for it on your running system. And if the running system has any of that stuff, you quarantine it. So isolate it and keep it from spreading. And so here's the example. You basically collect cryptographic hashes of every known malicious payload. And then if that malicious payload shows up on your system, you basically delete it or you disable the system. And so that's the signature detection approach. One of the good things about signature detection is that there are very few false positives. If you have a file with a known bad hash, like you're not going to have a good file that automatically collides with that hash because of the hash function is typically collision resistant. So anything that you identify as being bad is pretty much 100% guaranteed to be bad. And that's the benefit of this approach. But there are a whole bunch of ways to get false negatives. And so false negatives are malicious pieces of software that don't have a known signature. And so it's really easy to bypass signature detection schemes. And this is their Achilles heel. So you could find a bad piece of software and say, okay, this hash, because this is a malicious piece of software, I'm gonna deny or I'm gonna filter and protect my systems from it. But then this malware could basically, so it's got a birthday hat in this instance, but the malware could just change its hat. And then unless you have generated SHA hashes on every single variant, this thing gets through. And this is the false negative. And this is where signature detection schemes really fall over because of the ability to do, to generate instances that are basically, that fall through.
Throw like a couple garbage bits in and then it's different.
Yep. Yep. So this is an approach that we had in the 90s. And then this is where your regular expression stuff comes in, because there will be some invariants in every piece of malware, and you would have to have a really good regex to make sure your regex matches only malicious variants and nothing innocuous. That's hard to do. And this is why this better not be the only tool in your toolkit. This should be one of them, right? Like as long as it doesn't impact performance, you should do some of this stuff just to get the known bad stuff out of it. But yeah, this can't be your only thing. And this is when we went all the way back and talked about defense in depth. So this is why all of these schemes I'm talking about, they're all integrated in the EDR solution, because the EDR solution is trying to do defense in depth, and there will be some signature detection kinds of things in an EDR, but there'll be other things as well that we'll cover. So just to show you how easy it is to confuse signatures, you can use an alias to confuse them. So you could say in my payload, say it's a malicious script, I have bin bash in there, and the SHA-256 sum of it is this. But if I modify the script and say, oh, I actually wanted /bin bash, this is the exact same file, different SHA-256 sum. And then I could use /bin/bash, got a different SHA-256 sum, does the exact same thing. So these are all aliases to the exact same command. Or you could do something at the lowest level. So these are like if you have a binary and you want to transform the binary so that it no longer has a signature that can be detected, you could change all your move L zeros into a register to XORs of that register against itself. And so this is called polymorphic code. Functionally, it's the same, but because you have changed the opcode for this one assembly command, you completely change the signature. So that's really easy to do. Another thing you can do is to use alternative but equivalent programs. So here's the hash of an exec of bin bash. So say the malicious software is trying to run bin bash. It's got a particular SHA sum, but then what happens if I change that to a different shell? Say I want to use Z shell instead of bash, different checksum, or I could use bin shell, or I could use bin TC shell, or I can use C shell, or I could use corn shell, or, oh, that's all I have. So again, they're different programs, but they do the equivalent thing for an adversary potentially. You can store code on disk in an obfuscated, potentially encrypted polymorphic format. And the thing that we cover in the malware class are these packers and unpackers. And the idea here is that whenever you pack a binary, you create a unique payload that's encrypted and compressed. And then the key is included in the binary, but it's different for every instance of the thing you packed. And then anytime you run the packer, you generate a new signature. And you just use software tools to basically create unique malware every single time. And this completely wrecks signature detection schemes. You basically have to unpack everything and then do signature detection, because otherwise it's going to look different no matter what you do. And these are examples of packers that you might come across. And then another bypass is to use metamorphic code. And so this is a strategy where you're just transforming the code itself every time you spread the malware from one machine to the next. You change some of its functionality while it's being reproduced. And this will also bypass signature detection. And so one of the most famous examples of metamorphic code is this Stuxnet malware, where the Stuxnet piece of malware only activated itself when it was in this nuclear enrichment facility. It actually looked around in its environment, and based on what the environment it was in, it activated particular pieces of code as part of the library of running it. So again, this is making sure that the signature detection fails because you've changed some things. Another really popular example of this is cheat software in games. And so if you are cheat software trying to hide yourself from the publisher of your game detecting you, then what you could do is write cheat software that basically disables itself whenever it's being run within a game company's servers. Like if you're running in an IP range of Blizzard, then you would just say exit out, so that the reverse engineer never sees the malicious cheat being run. And then Blizzard, the anti-cheat software vendors, are doing the exact same things to the cheat software, where they're like, I'm only going to run certain checks on certain machines so that the adversary never sees the full complement of my anti-cheat techniques in one place. And so this is using metamorphism in order to do this kind of activity. Okay. So one of the things that this should hopefully drive home to you is that you're going to need to do some kind of heuristics to avoid signature explosion. What you're going to have to do is look for invariants across your malware samples, and then use those invariants as part of your signature, and not just a straight up SHA-256 hash of the malware itself. And this is where that regex stuff that we did earlier, that's where you need it, because you're going to have to look for that kind of pattern matching in order to identify malicious versus non-malicious. Okay, this signature detection function is so complex that they now have signature detection as a service and malware detection as a service. And this is what VirusTotal is intending to do. It's basically a cloud-based antivirus solution, because every one of these vendors, so in this case, there are 70 antivirus vendors. Each one of these 70 vendors has a different library of known bad signatures. And so then the idea is, can we leverage the power of the crowds to get a good signature detection scheme? So this is defense in depth by using a whole bunch of vendors. And this is what the innovation of VirusTotal was. where basically, well, this is owned by Google now. Google will run all of the different engines against a piece of malware. And so the idea is that you have a sample and you're like, what is this thing? You upload it to VirusTotal, and then Google will basically detonate it, analyze it, and then give you a report back as to what this thing is, and then you can clean it out of your system. Is basically the idea of this. Okay. Another thing an EDR system might have is a way to sanitize all of the incoming data on that endpoint. So there's this set of tools called content disarm and reconstruction. And this has got this acronym CDR. And the idea is that if you have an incoming piece of payload, you're going to basically remove anything that looks dangerous that could potentially result in code execution on your system. And so I don't know if you've seen this where you download like a document from the internet, and when you launch the thing, it basically gives you it in crippled mode. Say, I'm going to remove all the macros. If it's a Word document, all the executable content, I'm just going to remove it. This is basically what content disarm and reconstruction is doing, because you can get code execution from viewing a PDF, from viewing a Word document, from watching a video, from viewing some images, in fact. So some image formats are vulnerable. And so you have a vendor who knows about all of these content-based attacks. And what they'll do is they'll take the unknown payload and they'll go through all of the places where code execution has happened in this content, and they'll sanitize it. They might transcode it. They'll remove all the scripts. They'll remove all the macros. They'll do any executable content and they'll just get rid of it in that payload. And then they'll reconstruct it in a static, innocuous, hopefully innocuous format for your employees to look at. So that's the idea. This is a picture of this. This is an architecture figure from one of the companies that does this thing. So you have an unknown file, you deconstruct it, you basically take all the individual components, and you could do signature detection on this stuff, but you're basically going to remove anything that looks suspicious, and then you're going to put it back together in an innocuous payload that you can then, for example, let the HR department double click on. So this is what you would put in front of your HR department. You would take all of the incoming resumes and you would do this and reconstruct it so that when the HR department is double clicking on that attachment, it won't lead to code execution on this thing. Okay, so that's signature detection and file reconstruction. I mentioned defense in depth. So the problem with signature detection, identifying known bad, is that the known bad could basically be millions. And this is a picture of the growth in the number of signatures over time. And this is from the last decade, but this is an exponential curve that just keeps on going up, right? Because now every piece of malware can be unique if you're doing just naive signatures. And so another way of doing malicious detection is to do anomaly detection. And with anomaly detection, the idea is that you take and identify known system behavior, typical system behavior. So you're monitoring all of your systems, saying, how is this system typically used? And then any deviations from known good behavior, this is basically spotted as an anomaly, and then you can do an alert and then deal with the anomaly. And so then you would eliminate or prevent the anomalous pieces of this. And so this is basically a big game of this big bird thing. So this is one of the things, like, I don't know if any of you grew up on Sesame Street. You're like, oh, I can do this. One of these things is not like the other, is basically what you're doing with anomaly detection. Okay, so this is actually modeled after the immune system. So the human body should know, I mean, assuming you don't have an autoimmune condition, the human body knows what the legitimate tissues and the cells are of itself. And then it can identify anomalies as things that it has to attack with its white cells. And so that's the idea of like doing that approach, but modeling it, bringing it over to computing systems is the idea of anomaly detection. And this was pioneered in 1996 in this paper. And the idea was to apply this sense of self to Unix processes that were legitimate. So you bring up a Unix system and you run all of the processes in this system, and then you monitor it. You're like, well, what is the behavior of every single process? And in this approach, you're modeling sequences of system calls that a process is going to make. And if you see a process deviate from a known pattern of system calls, then you stop that process, is the approach. And so this is a picture of what they did. So you run, say, a web server, and then you monitor the web server. You throw a workload at this web server, and you can see the system call trace sequences. So after an open call, this is followed by sequences of read, mmap, and mmap, or get rlimit and then close. And so you could do this for every single sequence of system calls. So if you start with a read, then the next 3 system calls will be mmap, mmap, and open. So you can see that that's part of this sequence, but then it's followed by a next one, and so on. So for every system call, you get a good idea of what the sequences should be for that process. And then if someone takes hijacks this process and attempts to do something different, then you'll automatically shut this process down, is the idea. So that's very powerful. You could do the exact same thing on network connections, right? If you're a web server and all you're doing is receiving inbound port 80, if you all of a sudden want to do an outbound SSH, that's going to look anomalous. And that's what that's the idea of this lysis system, is like you're going to do the same thing. You're going to monitor all the incoming connections, and you're going to see incoming port 80 all the time. And then whenever you see an outgoing SSH or an outgoing FTP, then you're going to use this immune system model to say, hey, this thing never does outgoing connections. I'm going to drop this connection, or I'm going to rate limit this connection because it deviates from something that I've typically seen on this particular host. And that's a very powerful anomaly detection approach that you can incorporate. This has gone big time with machine learning over the last 5 or 6 years. This is what they're doing now. They're applying all of the machine learning tricks in the toolkit to do anomaly detection across all sorts of network traffic. And so here are on the right, so these are the different classes of anomaly-based or classification systems in machine learning and AI. And so you can apply any one of these different techniques to do this kind of anomaly detection. And that's what the industry is doing, a lot of these sort of startup companies. And so what this does, if you're an adversary and you're looking at this, what would you need to do as an adversary to go undetected? Well, what you need to do is something called a mimicry attack. You're basically going to have to get on that system. You're going to have to monitor what legitimate activity looks like, and then you're going to have to blend in. And so this is the mimicry of good things is what adversaries now have to do to hide from anomaly detection. Okay. So all of this is evolved into this, what we have now is the endpoint detection and response system. And this is basically the modern approach for doing malware detection on hosts. And so the sequence is to monitor your endpoints for all these behaviors and to build a huge model. And that's what this looks like. You take all your endpoints, you collect all the data from the execution of these endpoints into a big old back-end data warehouse. And then you run some kind of machine learning algorithm on top of all this data. And then from here, if you have a malicious or an anomalous thing that happens, where maybe this endpoint gets hijacked by a threat actor, this behavioral data will be compared against this profile. And then based on this, you can then do this remediation. So you can basically quarantine this device, or you could have an IT staff get an alert, and then they can actually do this remediation manually. So that's basically what EDR is intending to do. So the next thing I want to talk about are these things called canary tokens. And these are ways of generating anomalies that are high fidelity. If you see an anomaly that's a result of a canary token, you know you've been compromised. And so the idea of canary tokens is, oh shoot, hang on one second as I get my system back up. The idea of canary tokens is to place resources around the host and around the network that should never be accessed. So these are all bogus things that if they are accessed and utilized, you know that this is because of an adversary accessing them. And so any access is going to trigger an alert, and that alert is going to have high fidelity because of the way these canary tokens were basically developed, placed. And this really makes things hard on an adversary, because the adversary, when they look at this token, they can't tell whether or not it's fake or if it's real, because this is part of their discovery process. And before using that credential, it looks like it looks like a good credential. Okay, so this is a picture of this. And so you put these green things, these are canaries, and these canaries should never be accessed. They're injected into the enterprise by the tool. And then as soon as a machine accesses one of these things, this is where the alert gets generated. And so the canary.tools, the Thinkst Canaries is basically the company that developed these things, but they open sourced a bunch of their canaries. And so you could actually use this without paying money potentially. Here is a cartoon flowchart. So, I like showing things in cartoons. This is a cartoon flowchart of how to use a canary token. And so this is, we're going to talk about how this can be used to basically deploy AWS API keys as canaries. And then as soon as any one of these keys is compromised, someone has access to the machine that they're on. And so this is what a canary is. You're generating fake either documents or tokens that look like the legitimate thing, but they're injected by the administrator. And then you sprinkle these canaries all over your deployment. So if it's in your Git repo, CI/CD pipeline, in a developer system, on your running web servers, inside of your databases, this is where you insert your canaries. And then the canaries themselves, they could either be URLs, they could be PDF files, they could be actual AWS security credentials. And then this is where if an adversary actually is on any of your systems and gets one of these canaries and tries to use it, this is where you can then identify where the compromise happened and that a compromise has happened. And that's basically the magic of what the canary token is trying to do. So here's an example with AWS API key tokens. And this is something, if you have a cloud project and you're trying to protect thousands of resources on your cloud project, and you're like, I can't monitor all of these things. What you would instead do is create a canary token and then basically distribute these things all over your cloud project. And so one of the things that they've done with canary tokens is they basically have these automated Terraform templates. So Terraform is a programmatic way of deploying infrastructure. You can use Terraform to programmatically deploy bogus data in your cloud project. And that's what this GG Canary thing is doing. And then you sprinkle these all throughout your AWS project. And then when this particular adversary gets access to these deployed canary tokens, then an AWS key is hard to resist for an adversary, because that basically could get you the keys to the entire kingdom, or it could be a canary. And if you access it, this is when the administrator can shut everything down, or shut down the system where this canary token got placed on, because then it was a compromise. And so this is the overall approach for a canary token. Okay, other questions about this?
I was just gonna say, we do something similar to this at OIT, where we created a bunch of fake Odin accounts. And then every time we get a phishing email going around, we give a bunch of the credentials to the phishing link.
Oh, nice.
And we just walked over the next week, like when people log in with the fake accounts.
Oh, okay.
Where it came from.
And then do you like
just
blacklist? You okay?
Blacklist.
Okay. So I'm curious with those fake accounts is whether they're accessing them from like AWS infrastructure.
Yeah,
they are. Okay.
Stuff.
Okay. So one of the things, if you remember the network intelligence thing, to detect whether the connection is coming from a proxy, a Tor node, or a data center, that would be something to just straight up deny. And then you do all day long? Okay, cool. Okay, cool. Yeah, and then like if you do that to get rid of that cruft, then you can get the adversaries who are actually using stepping stones inside.
Almost always it comes from like other organizations, like they'll get a hold of a machine at like, just for example, like another university or something, and then they'll use that to access a machine in our university.
Okay.
So at first glance, it's kind of like, oh, like it's just another school like accessing us. But yeah, it's because they just have footholds in a lot of places.
Okay. And then when you identify a machine in another university, do you actually contact the abuse team?
I don't personally, but yeah.
That's the idea.
You can kind of trace it back and just be like, hey, you have a suspicious, like a lot of spam email gets generated from, like university emails.
Okay, yeah.
Because they don't get filtered as much. If you have like a .edu, Gmail doesn't like filter that. So they get a lot more traction.
Interesting. Yeah, so a canary account. Canary tokens don't have that facility, but yeah, if you have canary accounts, that would definitely be something to monitor. Yeah. Okay, another thing you can deploy on the end host is memory integrity monitoring and enforcement. So we talked about process hollowing and process injection earlier. And so one way to detect that kind of activity is to continuously monitor the integrity of all the process's memory throughout time. And if you do that, then you can detect when things like LSAS, which was one of the, I think this is the WannaCry thing, things like LSAS have been hijacked. So in this case, this LSAS process has a page that doesn't map to an underlying DLL or binary. And this is basically where they've injected a memory page, delivered the malware in memory, and then basically did a process injection to turn LSAS into a zombie. And if you're monitoring memory continuously, looking for things like this, you can immediately detect that process injection technique. Another thing you can do, so that was process injection. You can also look for processes that have been hijacked, and where you basically inject a page and you write to that page and then you start executing from that page. And so that's another technique for doing process injection. And in this case, having a memory segment that's readable, writable, and executable indicates malware. Because typically when you run a program, the executable parts of memory are only readable. And so if the adversary is doing the injection, they need a writable page. And so they'll make a page that's readable and writable, and then they'll turn on the execute bit. And that's a sure sign that some code injection has happened on that process. Now, if the adversary removes the write bit and then makes it readable and executable again, then you have to go back to the other detection technique. Okay. You could also, so that's the monitoring approach. You could also prevent the modification of program memory for critical services. You're like, you know what? These blessed services that are allowed to run without me checking them, I got to make sure they can't be tampered with. And so this is what Windows Defender System Guard started doing in 2018. They allowed you to turn on this memory integrity flag. And what this memory integrity flag does is it basically protects the process by virtualizing it. And so it basically creates allows this process to run in its own little virtual machine. And then that prevents other processes from going and accessing the memory and modifying the memory of that process. So this is what it looks like. You would have, this is basically before, where all of the apps are sharing the same kernel, and then apps can basically write into the memory of other apps. And so the idea is for specific critical services, you would basically create this secure mode that basically is doing this code integrity thing that basically prevents the memory segments from being tampered with as a separate thing. And this is the kind of virtualization and isolation that we'll talk about later as being used to protect systems. Another thing to do is to extend this to the file system. So you're protecting the memory segments. You should also protect the file system from people dropping Trojans. So Trojan versions of these system commands should also be identified and removed. And so this is something called file integrity monitoring, or FIM. And so you basically are examining the server for the contents of all the files that are on them. And then anything that gets changed, you have some management server trying to figure out whether or not those changes are legitimate. And if you see that a critical command that shouldn't be changed has been changed, then you would basically issue a real-time notification. So the most famous example of this is Tripwire, which has got a local office here in, well, they just got acquired. So now they're called something else. But this is the idea of Tripwire. And so what they do is they basically do SHA-256 sums of all of the legitimate files that they want on their system. And then anything that doesn't match, they alert you on. So if someone changes that file and the hash changes as a result, then you would raise that alarm and then get that notification. The problem with this kind of approach is false negatives, because well, one of the things is false negatives because this assumes that the original file hash was actually good and wasn't already compromised by the adversary. So this is just more of a change detection service rather than a sort of a malicious software detector, because you have to assume that the original file was actually didn't have any vulnerabilities and didn't already have a backdoor installed already into it already. It also leads to a whole bunch of false positives. And this is more damaging because an administrator, as soon as you get a couple of these false positives, you're going to stop paying attention to the tool. And so if you have this monitoring system files that actually do change all the time, or if you're automatically updating the software on your systems, and that's part of your operation is to patch and update, you don't want this tool to alert you on those things. Otherwise, you have this the signal to noise ratio is too great. Okay, so both FIM and then the process monitoring, those are things that are often rolled into these IDS and EDR systems as well. Okay, so that is all for all of the monitoring techniques that you might come across. I'm going to now transition to another class of techniques that people are using to protect hosts. And the idea here is to do something called trusted computing, which is to basically restrict the programs that are being executed on every single host. So the easiest thing to do is something called allow listing. So if you're on a system and that system has a very restricted set of programs that are legitimately used to run, then you should create this allow list, and anything that is not on that allow list, you block. So this is the example. You allow these particular good programs to run, and then anything that is not on the list, like these two things, you would just say, I'm going to block that. And so this is basically what's happening. You're getting all of this malicious content interleaved in with legitimate content. And anything that's not on this green clipboard is basically denied access. And so there are companies that will provide you this facility So AirLock Digital, Microsoft App Locker, Windows Defender application controls. You can set up systems that say, these are the blessed pieces of software this particular system is allowed to run. Deny everything else is the approach. Okay. There are different levels of allow listing. You could just do binaries only, just programs, or you could do binaries and the libraries that they depend upon. A lot of attacks come in through libraries, and so this is where you would want both the binary and the library involved in the application control. You could also restrict execution on the allow list based on the user. So an administrator is allowed to run certain commands, but maybe a regular user is not. And this is just a level of a finer granularity access control versus just a straight up allow list that's global. So that's something. Allow lists have an issue here. How do you ensure allow lists specify authentic programs? And what happens if the adversary replaces this legitimate program with a Trojan? And so you need to make sure that you do something not just on the allow list that says these programs are blessed. You have to also ensure the integrity of the program that's on that allow list. And so usually with the name of the program, you are attaching some kind of integrity code, a MAC that says, this is the name of the program that's allowed to run, as long as it has this hash, this integrity hash, and then you would allow those things. An extension to this is code signing. So with code signing, you're basically establishing a software chain of trust using signing keys from the firmware to the bootloader, to the operating system kernel, to the application developer. And so this is basically implementing this chain of trust. And there are examples of this. So both the Apple and Android app stores, in order for you to run a blessed app, it has to be signed. It has to be vetted by one of these two app stores. Otherwise, your phone's going to complain. The same thing with Linux. When you do an apt, it basically, your default Linux system trusts the signing keys of the repositories you've asked it to trust. And then when you do an apt install, it makes sure the packages that do get installed have been signed by the repository you trust. So you have the public keys of all these repositories, and then you validate the signature of any package that you install, assuming that that repository is going to sign those packages. Windows Update has this as well. The secure boot facility on most of these systems, they're using code signing as well to validate the authenticity of all the code that's running. Okay, so I'm going to just cover a little bit of how this works with secure boot. Secure boot allows you to establish a chain of trust from the hardware through the bootloader all the way up through the operating system, and then finally to any of the applications that run these things. And basically, there are signing keys where based on the hardware, so you have basically the public key of trusted providers in the hardware, and then you deliver software that's signed by that trusted key, and only if it is signed will you allow it to load the next step of the process. And then from the bootloader, you have trusted bootloaders, and then only with the private key signing the secondary bootloader are you allowed to go to the next step. And so this trust is anchored all the way through to the hardware vendor, and that's how you establish the chain. This is best shown as this animation, where you basically have starting from the firmware, the UEFI firmware, this thing will only load firmwares that have been signed by the hardware vendor. And then from the UEFI firmware, this thing is only going to load bootloaders that have been signed by trusted by this particular trusted UEFI vendor. And likewise, all the way up to the top of the stack. And so you're using these certificates and these private keys and the signing keys in a different way than we did TLS, where you're establishing it through software rather than through certificate authorities back to the client. Okay, and so you see this is a signing chain, and this is something similar to DNSSEC, right? But it's just done through software rather than through servers is the idea. Okay, so I'm covering this because there are attacks, because we've deployed this pretty prevalently, and now adversaries need to find a different way to get their malicious code to run, right? Because there's no way they're going to get that thing signed otherwise. And so there are attacks to code signing approaches, and one of the ways to attack it is to compromise the signing key. So if you have access to a trusted signing key in any part of that secure boot chain, you can inject yourself into it. You could take code that has been signed, and if it's vulnerable, you can basically hijack that trusted code in order to inject your malicious code into it. Or you could basically take the legitimate code and you could confuse it into doing something malicious. And this is kind of like a vulnerability, but there's this set of attacks called confused deputies, where you confuse the signed binary into doing something it probably didn't know it wanted to, or it probably didn't want to do. Okay, so we're going to talk about all of these different things. And so one of the ways that you could basically, the first thing is hijack the signing key. And so here is this was last month. This particular vulnerability got released where you could actually bypass the crypto API of Windows systems using a specially crafted certificate. This allows you to bypass the signing key. It allows you to say, I'm going to let you run untrusted code by crafting a certificate that looks valid, that passes the validity check. So this is an example of the first one. The other mechanism is this lulbin mechanism, and this stands for living off the land binary. You're basically going to use pre-installed signed binaries to execute malicious payloads. And examples of this would be to hijack bin bash or PowerShell on Windows, because all of these things are allowed to run. Those are trusted. So if you can deliver your malicious payload by getting these things to run, these legitimate pieces of software to run that illegitimate payload, then you get bypass the code signing as well. Okay, so here's an example of a lulbin. So one of the things that has been done to bypass the App Store, and this is in particular the iOS App Store, is that there is this signed binary called test flight, which allows legitimate providers to bypass security checks in order to test their application. And so what malicious malware has done is said, hey, as part of executing my app, I want you to install test flight. And so this has been blessed by the App Store. And so if you download this along with the malicious payload, this is how that malicious payload can use a trusted piece of software to run its malicious software. So that's just an example of doing this this lulbin basically. Another one is to compromise a vulnerable binary. So in this case, there's this very famous Genshin Impact anti-cheat system. This thing has a legitimate signing key, but is so vulnerable that installing this will basically allow anyone access to your system. And the developer no longer maintains this piece of software. And so it's got a legitimate key. It's highly vulnerable. And so adversaries are like, oh, well, this I could just basically attach my malware to this driver and then distribute it. And then users, when they launch it, it's basically signed, but because it's so vulnerable, the malicious author can get complete access to that system. And so this is another, just because it's signed doesn't mean you're safe, is the idea of this particular thing. And then this one has been in the news. This is basically a bug in the signing verification. And so this is something called Felina, where basically you can send a Microsoft Office document, and it ends up the bug in the document allows you to execute arbitrary PowerShell commands. And so it's basically hijacking a legitimate binary to do the malicious thing because of errors in this internal protocol handler. And that's effectively a lull bin because it's using PowerShell for it. So this is an example of it. It's basically hijacking this protocol handler, and then you can see it's actually going to invoke this particular binary that's pre-installed on and blessed on the underlying Windows system below, and that's what you see here for this process. Okay, the next countermeasure that I want to talk about is reducing the attack surface of your enterprise. You had in your labs a whole bunch of these, right? And you did this for a single server. What you want to do, though, is to do this across your entire enterprise. And so it's a pretty manual process to basically poke around a Linux server and then see all the vulnerable processes and to disable them. But this is something that enterprises are being mandated to do by places like CISA, it's recommended that they do this by places like CISA. And so there are now a lot of tools that will automatically perform an audit of everything you're running. And so that would be the first part of this. And so here's an example of a tool called Run Zero, where it basically you plug it into your network and it just monitors everything that's on it. And it tries to detect everything that you currently have running. And it's basically doing application and operating system fingerprinting on all the traffic that it sees. And then it'll log these things. And so here's an example of the console. So you can see what it's done. It's just basically Shodan for your internal enterprise. It's basically collecting everything that you're running and then giving you a dashboard for all of the things that it has observed. So right down to the products that you're running, the kinds of things that you're running, the products that are running, the protocols that they use, everything is being collected. And when you get this inventory, then you can act on it. You can be like, oh, I'm running way too much stuff in my enterprise. I'm going to start removing some of these things. And that's basically what the reduction of attack surface is doing. So this is an example from your firewall set of slides. So you could do something that looks like this. You could actually filter the traffic, and then you keep these processes running, and then no traffic can reach them. But the better thing to do is to just remove the unused services altogether. And that's basically, that's where the scaffolding in your lab is. First, you can filter it, but then eventually you actually do want to just shut that service down. Okay. And I don't think I'm going to get to containment and isolation. I think I'll just stop early.